Yeah, so the theme of this talk is going to be, of course, trajectory prediction. That's what a lot of us are interested in here. But I want to talk about a concept that you can think of as system-level failures, which I'll define for you in a little bit, and I think is quite important when we think about the long-term deployment of these kinds of prediction models in the loop, especially with robotics and decision-making. But let's back up for a second and think a little bit about where we are. And I think I don't have to convince any of you that it's a really good time to be in robotics. It's a really good time to be in AI. And I think it's also a really good time to be in interactive technologies. Specifically, as I'm sure a lot of you know, like specifically these frontier AI models are allowing autonomous agents to interact with people at a scale that I just couldn't have perceived before in the past. I mean, when I started my PhD almost 10 years ago, I didn't expect that I could actually go and take a fully autonomous ride in a Waymo today. Actually, let me do a quick poll. How many of you have been in an autonomous car before? Okay, this is crazy. I mean, if I asked this question even a few years ago, I just wouldn't get this kind of response. And if you haven't experienced this, please fly to San Francisco and try it out yourself. It's really, really cool. But anyways, interaction between autonomous systems and people are even going beyond driving, right? We see this in interactions between, for example, LLM agents and people, these kinds of robot manipulators. And so it's really quite impressive. And in fact, I want to kind of argue that, this is the workshop on human motion prediction. And I'd actually argue that the broader field of trajectory forecasting, in fact, has laid the groundwork for a lot of these embodied foundation models we see today. For example, if we think about kind of the trajectory, no pun intended, of generative AI, there's foundational techniques that established the basis of a lot of the models we think about today. But if we really think about how these models were pushed, many of the domains that were embodied and were first explored were trajectory forecasting. For example, social GAN is an example of now an older paper that was using these modern generative AI tools for specifically embodied trajectory forecasting, embodied reasoning. And as our models and the way in which we represent complex data got more and more advanced, we also saw trajectory forecasting being able to be more and more advanced too. So there was this paper, for example, from Waymo called Motion LM, which essentially says, well, maybe forecasting can be thought of as next token prediction, the way that we think of language, where maybe small primitives and actions are essentially a vocabulary. And now you start seeing even these end-to-end models, like Drive LM, which are not just predicting the physical behavior of agents, but other properties of the environment or anomalies, like so many more things that you can predict. And I think the reason that these kinds of paradigms have been really exciting for trajectory forecasting is the fact that by consuming a lot of data about the world, specifically about people, you can learn latent representations of the world that are really hard to write down by hand. Like, it's really hard for me to know what's going on in your brain when you make a decision. I can try, and in fact, I have older work on this, but in general, it's a really, really hard modeling problem. And so the hope is that maybe by just consuming a lot of trajectory data of your behavior, I can infer this lower dimensional latent representation of your internal state with which I can then generate plausible futures about what you might do. This leads us naturally to another really nice aspect of these kinds of modeling paradigms, which is multimodality. The future is diverse, many things can happen, but I need a model expressive enough to capture these diverse futures. And last but certainly not least, a lot of these paradigms can be informed by many kinds of human data. Physical behavior, preference data, language, these are all mechanisms by which we can inform how we predict and even what we predict. At the same time, it's precisely these advances. It's precisely the fact that we have robots doing better because they are using these kinds of models that have gotten a lot of people concerned about the safety and alignment of human autonomy interaction. Now, one of the settings I like to go to at first, just to understand why this is a hard problem, is to go back to autonomous driving. I'm going to pick on our favorite company to pick on, Tesla. And here, this is an example of Tesla Autopilot that someone turned on while they were driving on the Bay Bridge. And the Tesla Autopilot decides to do a hard brake in the middle of the highway. Okay, this caused a multi-car pileup. I was actually in the Bay Area during this time. I was trying to go to San Francisco. Thankfully, no one was hurt, neither was I, but it caused a huge headache. And why I like this example is that you know, a lot of the times when we think about safety, we think about something like, oh, well, if you're going to collide, just stop. But here it's precisely stopping that caused this safety violation. It caused this failure. And it's because clearly the system did not understand the right context that if I stop, then other people might not be able to stop in time, and then we end up in this precarious situation. But one thing that's particularly interesting about robots that are deployed at scale with these kinds of predictive models is they have other kinds of safety concerns that aren't just collisions. Here's another example of a safety concern that might be harder to codify, and this will be another Tesla autopilot example as well. Okay, so this is a Tesla autopilot. It's merging onto the highway. It appears to be driving normally, but in the distance, there's a small plastic bag that's floating around, right there. Now, it doesn't look too crazy, but if we rewatch this scene, the vehicle tries to merge in and then aborts, right? Does that little swerve to get out of the way of the plastic bag. Now, even though nothing unsafe from the perspective of collisions happened, if I'm the passenger in the seat and my car is suddenly swerving, when I look at this plastic bag and I say, just keep going straight, just complete the merge, that's really scary for me. You know, I might either lose my sense of trust, maybe there's another vehicle behind me that's also like, why are you doing that? And cause a chain reaction, so on and so forth. In other words, the problem that happened here was that there was a misalignment basically between the human's representation of the world here, which is that this is a crushable bag, just drive over it, and the vehicle's representation. And this ultimately is what might cause a safety concern that maybe isn't just collision avoidance, but can lead to other things like inefficiencies or unpredictable behavior. Now, if I was to formalize a little bit more what makes this kind of problem really hard, what makes trusting a prediction model really hard, is it's characterizing this feedback loop between human stakeholders and the autonomous system. And this feedback loop is present at all parts of the robot's life cycle. It's present at training time, okay, where you're collecting data of feedback loops between multiple people, between people and robots. It's present at fine-tuning time, when people are saying, this is good, this is bad, I want to tweak the model parameters, I want to upweight this data. It's present at deployment time, where small tweaks in your prediction model or in your autonomy stack will cause really different behavior changes in the people you're interacting with. And as you can imagine, this influences the representations the robot builds, the representation the prediction model has, the decisions, and the responses. In other words, the safety of a predictive model can't really be determined in isolation. It's really, really entangled with the behavior of human users over time. And so today I want to touch a little bit on this question. I want to talk a little bit about how do we measure and how do we design prediction systems that are aware of these kinds of complicated feedback loops, these kinds of influence. And specifically here, we're talking about the influence of a predictive model on a robot's decision-making on another agent's behavior. All right, let's dig into what drives these deployment time feedback loops. So here we're going to look at this case of a human and a robot interacting in their environments, in their own embodiments. And you might see this in something like autonomous driving, home robots, things like that. And in general, the robot has some policy with which it makes decisions. This policy here is denoted by pi theta. Here, theta are the parameters of this planner. For example, if you're using a cost-based planner, these could be the weights of your cost function. If you're using a generative planner, it's the weights of your neural network. And in general, this policy here is going to generate some actions for the robot to take, given the current state of the world S. Some predictions, P phi, which are either explicit or implicit. Explicit meaning I give you a predictive model. Implicit meaning maybe my generative model just learns a joint distribution over everyone's behavior, and I just pick the most likely behavior from that as my plan. We'll talk about that later as well. And C is some context variable. For example, it can be the map of the environment, whatever else needs to be as part of the understanding of the task. And just to unpack this a little bit more, the human behavior predictor here is a mapping from some history of states, this is boldface S, the context, to some future actions the human might take. This is what happens inside the robot's mind, but in practice when you get deployed, the human's going to actually take some actions, AH, from their actual internal policy. And the robot does not have access to this. But when they interact during deployment time, this is what is inducing these feedback loops between how the robot's making decisions and how the human's reacting. And that's what's going to form this complicated dynamical system. And what we want to really understand is which prediction failures that my robot was relying on really mattered during the interaction. And maybe if I detect these, how can I improve my interaction model, my prediction model, over repeated interactions? Now, the way I like to think about this is imagine you're Waymo or you're another big company, and you've started to get your system to be really nice, ready to go, and you start deploying it. Every time you deploy your system, and here when I say system, I mean this is the composition of the predictor and the planner, you're collecting tons and tons of new data. This data is constantly growing. Okay? For example, Waymo, 20 million miles plus that they're constantly driving of real examples. This is growing every day as they are deployed. It is growing thanks to your data, because I know now many of you have contributed data by taking rides. The same kind of challenge happens also in language models too, by the way. If you ask ChatGPT for certain information, it'll tell you, oops, my last training data was here. I don't really know that yet, but you can get retrained and you can put more data in there as well. So these are natural ways in which your deployment data grows and changes. Another thing that happens, by the way, that's very important here too, is that there are naturally human interaction distribution shifts that happen over time. Maybe people start kind of beefing with your company. They don't love your cars that much. It's time to prank them. So you start having these weird new types of interactions, weird new type of data that you didn't anticipate before deployment. So at first it might be tempting. Let's just keep retraining our prediction models forever. Okay, I'm just constantly deploying my model. I'm constantly retraining it with every single thing I see. So for example, here is my predicted model before, P phi. I have this giant data set. It's constantly growing. I shove it all into my model, get P phi prime. The reality, though, is that if we want our production or deployment models to actually be useful, by useful here I mean they have fast inference times, they only know what matters, you can't keep shoving everything into the model. This model will have to infinitely grow forever. So you have to get kind of clever about what you are really remembering, what really mattered from the deployments. Now, one other thing you could do is you could say, well, okay, let's do a more targeted thing. Let's look at a subset of this data, and let's only look at a subset of the data which exhibits high prediction errors. And then let's retrain just on this data. However, I think we should take a closer look at exactly what this data contains. All right, here are two scenarios. And what we're going to see is, this is a physical instantiation of a robot predictor and planner around a person. And here are two scenarios. In one case, the robot predicts that the person's going to keep moving forward, and so the robot's going to swerve around them to the right. On the right-hand side, the robot predicts the human is going to pass, and therefore the robot decides to go straight. The reality, the deployment time interaction, will look something like this. The human actually passes the robot like this on the left, and the human doesn't yield to the robot in the right. If you measured, let's say, the L2 deviation between the prediction and the plan of the predicted motion of the human and the actual motion of the human, you would see that both of these have the same L2 error. By the way, this is also a common metric for training trajectory forecasting models, ADE or FDE. And these two might have exactly the same error, but they led to very different consequences. Right? So not all open loop errors have the same closed loop consequences. On the right-hand side, we had this worst case collision, best case awkward interaction. On the left-hand side, nothing that bad happened. Here's another example from autonomous driving. I know these figures are kind of complicated. The blue agent is the robot in this case. The white and gray agents are human vehicles. The predictions are shown as these gray tendrils coming out of each agent, and the actual executed robot trajectory is shown in blue. And then the actual executed trajectory of the other vehicles is shown in like the opaque images over time. Now, if you look at the types of errors that are shown here, I'll break them down for you. On the left-hand side, here, this parked car on the lower right is predicted to move, but it doesn't, it's parked. On the top here, this stranded truck is predicted to accelerate, but it won't. And on the lower right-hand side, this center white car here is predicted to change lanes. You see those gray tendrils moving to the right, but in reality, it doesn't change lanes. if you look at what the robot actually does in each of these closed loop interactions, on the left-hand side, nothing bad happens. The robot just keeps going straight. On the right-hand side here, the robot has a head-on collision with this stranded vehicle. And in the lower right here, there's a huge inefficiency. The robot's getting bullied. It is getting bullied by hallucinations that this other car is definitely going to merge. Which, by the way, I think this is very important, right? When we're talking about system-level failures, these kinds of closed-loop consequences, it's not just collisions. These kinds of inefficiencies are also failures of the system that are caused by a poor prediction model. And if you think about, I mean, this is a toy example, right, in a controlled simulator that we're using here that I'm going to show you about more later, but if you think about genuinely scaling an autonomous system, while it doesn't seem that bad, the number of erroneous predictions your robot is going to encounter in the wild is enormous. Think about driving through Times Square. I mean, so many pedestrians, so many agents around here, many of whom you're probably doing a terrible job of predicting. Are you going to waste your model's capacity to worry about every single possible person in that scene and what exactly they could possibly do? That seems a little foolish from intuition, right? We only want to attend to those agents and those mispredictions that really, really, really matter. In other words, a more targeted thing we should do, maybe, is look at a subset of this data which exhibit, oh, so this is what I mean, by the way. So you might waste capacity on learning irrelevant behaviors that don't actually matter that much. And so instead, what we might want to do is think about the existence of this extremely important subset of these prediction errors that actually influence the robot's decisions. I'm going to call these system-level prediction failures. I'm calling these actually based on some terminology from a really nice line of work that Professor Marco Pavone's group has also been working on. So they have a really nice paper called A System-Level View of Out-of-Distribution Data in Robotics. It's linked down there. And they also have some work related to system-level errors and trajectory forecasting too. And this is kind of our contribution to this line of work. The main challenge is how do you actually quantify, how do you automatically detect that a system-level prediction failure has happened? And what value does this data really have for improving? And the key idea that we explored in this work was the mathematical notion of regret is a principled way to detect the degree to which a prediction error influenced or degraded the robot's performance. So for those of you who don't remember the definition of regret, it looks something like this. So let's break it down. So you have some reward function. This is the robot's reward function parametrized by some parameters theta. This is the actual observed set of actions for each human, H1 to HM, if there are M agents in the scene. The actual observed state trajectory S hat. And this AR hat is the actual executed robot behavior. So this is your deployment data that you measure. Now what you're doing is you're saying, well, let me replay that data from the other agents and think, now that I know what they actually did, is there a better decision I could have done in hindsight? Essentially, can I maximize AR given the fixed behavior of the other agents? Right, and I'm going to compare that to the reward of the executed behavior that I actually performed in the real world. And to build some intuition for this, I'll show you, this is a figure taken from one of Marco Pavone's papers as well, so you should definitely check that out, but I'm just going to instantiate the regret metric in the context of this nice example they had. So here on the left-hand side, if you think about, maybe actually let me step through this first of all. So here the robot decides to go forward, but the human does a lane change. And the human does a lane change which is erroneous with respect to the prediction of keeping just their own lane. So if you were to actually evaluate the regret here, I'm sure we would all say, well, in hindsight, I have a lot of regret. I would have slowed down now that I know that they did this aggressive lane change with me. On the other hand, if you looked at this other scenario where the prediction was just the person keeps their lane and the reality is that they switch lanes to the other lane, you don't have that much regret. In hindsight, I would still have moved forward. I wouldn't have slowed down. And this is precisely disentangling what is a system-level failure or not. So there's one little feature, though, here, which is that while regret is a principled measure of detecting these kinds of differences in prediction errors, there are still a few challenges in practice. One is that not all modern robot planners use reward functions. For example, this motion LM model can be used as a planner, as a generative planner, in fact, by just fitting a joint distribution to everyone's behaviors and choosing the most likely behaviors for you as the robot, in response to everyone else as well. So now you actually don't even know what the reward function is for evaluating regret. Also, standard regret we found when we deployed into different scenes can be miscalibrated between really different deployment contexts. And that's because the reward scales are not the same. If I'm driving in a really, really open environment versus a super crowded environment, what it means to kind of penalize myself is going to look very different. It's going to be normalized for that particular context. And so here we had one more idea, which just says, let's evaluate actually the quality of a decision. Let's compute regret in the likelihood space rather than in the reward space. So we're going to take that equation from before, and now what we're going to do is we're going to actually evaluate the probability of an action that the robot could take given some context or given some interaction history. And this probability distribution can be obtained in a variety of ways. I'm happy to talk about that more. And these theta parameters here can be shared also with the planner. So for example, if you're in that generative modeling case. And so the nice thing about this here is that essentially the probabilities now kind of scale anomalies with respect to the context that you're in, and you don't need an explicit reward model, so maybe you can open up opportunities for anomaly detection with generative planners that do not have explicit reward functions. And in fact, these examples I showed you before, these scenarios actually had a generative joint planning and prediction model that we used in hardware here. And you can see that the high regret scenarios where in this case, a collision happens because of the incorrect predictions, are assigned a much higher regret, 0.31, compared to these non-system level failures, which have relatively low regret. So we've talked a little bit about how to rigorously quantify system level interaction errors, but let's talk a little bit about what value this might have for improving. In this particular work, what we're going to do is we're going to go to a simulator, since we can do closed loop deployments in simulation, because I don't actually have a robot fleet to actually do a closed loop deployment with. Here, the robot is going to be using Agent Former, an off-the-shelf trajectory forecasting model. It's been pre-trained on the new scenes data set. We're going to use this tree policy planning model as our robot planner, and then we're using the BITS simulator. This was released as, partially by NVIDIA to do our closed loop deployment, to get our deployment data set. And what we're going to do is we're going to fine-tune our trajectory forecasting model with different data compositions. Maybe we'll only give it low regret data in one scenario. Maybe we'll randomly select data. Maybe we'll only show it high regret interactions. And then on the right-hand side, we'll show it everything. So like kind of the best we could ever do if we had a really, really big model that had capacity for memorizing everything. If we first look at just open loop prediction error, so this is the base model on the original data set, high regret and low regret interactions. And the first takeaway we really see is that if you essentially only fine-tune your prediction model on high regret interactions, you can still get prediction accuracy improvements both in high regret scenarios, and you do not decrease the performance of low regret scenarios. So this is really nice. This means that open loop, we're not damaging the model by focusing our attention only on high regret scenes. The next thing we looked at was closed loop evaluation. We redeploy our robot with the improved prediction model, and we say, okay, what happens now? So this is, for example, the base model is the one that collides with the vehicle and does this wrong thing. And here are qualitative results as a function of these different data sets. You see on this snapshot that as you start seeing more and more of the data, the fine-tuned model gets better and better. But look at the difference here between the model that sees significantly less. In fact, 77% less data, the high regret fine-tuning one, versus the all data set one. We're seeing comparable qualitative performance here, even though we're seeing 77% less data. And quantitatively, we see similar results here, that essentially high regret fine-tuning can improve the closed loop performance during redeployment. Last but not least, we see this interesting correlation that closed loop and open loop performance is only correlated in these high regret scenes. In other scenes, they're less correlated. If you're getting better in open loop, you may or may not be getting better in closed loop. And so the overall takeaway here is that the presence of high regret interactions, high regret data, is one of the most important indicators of redeployment improvement. If you want to check out more results and all of the details, please take a look at the image on the paper on the left-hand side here. And we also have some other work here at ICRA on the right-hand side, which is also related to system-level safe influence here at ICRA 2025. I want to say a quick thank you to all of my students and my funders, without whom this would not be possible, and I'm happy to take any questions.
Hi, Professor. Thank you for a great talk. So I really like the idea of like bringing in regret, and that way you don't need to train with all the data you have. Do you think training with regret and getting the more and more data like Waymo gets, can we get somewhere where there will never be accidents, or it's just impossible?
Yeah, I think that's kind of the gold standard we all want, is to never have failures, never have accidents. I think there might be a universe and there might be a paradigm in which you can do this extremely gradual deployment that's extremely careful, that never has this happen. But I think making failures is kind of a part of the engineering process. The question is how to mitigate it in a principled way and how to minimize these failures. I don't know if you can ever get zero. But I think the point is that we need to design resilient systems that do the most with those kinds of really, long tail events, and from a first principles perspective, try to minimize their potential. Yeah.
Thank you for the talk. So one issue with bringing this into the closed loop case is that we become dependent on the planning model that we're using. And you can imagine that different planning models might be more responsive or less responsive to these changes. Do you have thoughts on how to handle that?
Is there a particular thing you're looking for in terms of how to handle?
So from, say we're just as academics are writing papers and we want to compare our improvements versus the state of the art.
Yeah.
If our model might work really well, but then when somebody else tries it with their planner, it might be total trash. And I think to keep the field, rigorous, it would be good to have some sort of way to not get messy with the codependence on both prediction and planning.
It's tricky. I hear your concern for sure. I think there's two strategies you can employ. One is you can do something where you basically say, look, my job as a prediction forecasting engineer is to give you the best possible model I can. And then it's your job as a planner, like a planner team or whatever, to figure out the right integration. But I actually think that it's a really interesting frontier to think about a little bit more how you tighten those up. Like, how do you propagate information from a planner into the predictor? For example, it'd be really cool when you develop a prediction model to know its sensitivity to the planner. So as you make small tweaks to the planning architecture, how good is your predictor at kind of having the closed loop performance be good or bad? That could be a really interesting thing to think in the future. But I think it's a really hard problem in general to have them totally decoupled, because ultimately you want the overall system to actually be good, not just the prediction model in isolation. Any other follow-ups to that?
No, thank you.
Yeah, but you're totally right. It makes everything messy.